Welcome to Module 6. Today we will discuss running basic statistics in MATLAB. At the end of this lecture, students should be able to run some basic statistics, including correlations, linear regressions, t-tests, and repeated measures ANOVAs. You'll also understand some of the basic structures of the functions that are used to run these statistics. You'll also create figures that summarize the statistical analyses and reflect significant differences. And then we're also going to build upon our abilities to sort data, select data, create new variables, and so forth. So to start, there are a whole bunch of basic statistical functions that are built into MATLAB and then elaborated in the statistical toolbox. So the first statistic that we're going to talk about is going to be a correlation. And the function that you're going to look for is cor. Then you can also run a linear regression, and that will be fit-lm. And there are a bunch of different ways to run analysis variance or ANOVAs. There's one-way analysis variance where you have only one variable or factor that's predicting changes in a different variable. You can have a two-way analysis variance in which you have two factors that are predicting an outcome measure. And you can have an n-way analysis variance, so anything greater than two factors of interest can be run using the ANOVA n function. The AOC tool is an interactive analysis of covariance, and we won't actually go through this ourselves today, but each of these different ANOVA functions can be pretty straightforward and worth looking at. Today we're going to cover a slightly more complicated statistical analysis using repeated measures model, which builds upon the basic ANOVA functions. And then lastly, there's also a one-way multivariate analysis of variance, or MANOVA1. And we will not go through that today as well, but it's just good for you to know that that exists. So let's go ahead and go to MATLAB. Okay, so here's my MATLAB window. We're in the right folder for this analysis, and we're going to actually load the data from a physical activity study. So these data have all of the data for each class subset by different days of the week, meaning intervention days and non-intervention days. So intervention days are going to be on Tuesday and Thursdays, and the non-intervention days are going to be on Wednesdays. And there are 4 classrooms, classroom B, C, D, and E. And there are 5 weeks of data. So the first thing we want to do is we want to remove our outliers, which may affect our analyses. So as we talked about in a previous lecture, we're going to look for any time that sedentary percentage from the accelerometers is greater than 0.9 or 90% of the time, because it's likely that that's not real data. And then we're going to set all the accelerometer data, which are in columns 7 through 16, to NANs. So I'm going to go ahead and run that. And then the next thing I'm going to do is I'm going to separate our data into all of the classrooms for the intervention days, which are Tuesday, Thursdays, and all of the classrooms and weeks for the Wednesday data. So in order to do that, we're going to use our logical operator to select which rows of data we want. And so I'm creating 2 new variables, PA data Tuesday, Thursday, and PA data W for Wednesday. And that's going to correspond to the rows in which PA data days of the week is equal to 1 for Tuesday, Thursdays, or PA data dot days of the week equal 2. So I'm going to go ahead and run that. So the next thing I'm going to do is I'm going to use the correlation function to compute correlations between the sedentary percentage and age. So the first thing is just to see whether or not we think that the participant's age actually affects sedentary percentage. So maybe younger kids are more sedentary or older kids are more sedentary. So now that we have our data subset for the days of the week equal to Tuesday and Thursday, now what I want to do is separate it out just for the first week of data. So here what I'm doing is, again, this is a little bit redundant, but the day of the week, of course, should be equal to 1, and the week of the intervention should be equal to 1. So this should give us just week 1, Tuesday, Thursday data. So I've run this now. And I just want to make sure that this has 52 rows, so PA data Tuesday, Thursday, and indeed it has 52 rows and 20 columns of data. And if we look at that data set, we'll see that some subjects have NANs, which might mean that they might have missed that day. Okay, so the next thing I want to do is I want to run the correlation. And before we do that, let's actually go up to the MATLAB help window and look at the structure of the correlation function. So here we can see that the basic correlation function can take one input and can create one output. We've actually run this in one of the previous modules, just giving an idea of what different types of functions can do. In this case, we're going to have two inputs. One is going to be the age of the participant, and then the other one is going to be the sedentary percentage. And in addition to this correlation coefficient rho, we also want to know if that correlation coefficient is significant. So we also want the p-value. So on here, you can also see that there are examples of how this function can run, and you can see the output of this. And so if I have two matrices, X and Y, with multiple different columns of data, it's going to do pairwise correlations between all the individual variables. So this is kind of nice to be able to do this. One thing that we have to note, though, is that our data has some missing data in it, or has some NaNs. So now I have to kind of check to see how this function is going to be able to handle dealing with missing data. And so there's a couple different additional parameters that you can use. Type here would be changing the type of correlation. The default is a Pearson correlation, which is what we want, but you can also force it to do a Kendall correlation or a Spearman correlation for non-parametric statistics. And in this case, it's going to take rows complete, which means that it's not going to take any data that is missing anything. So if I'm missing the age of the participant, or I'm missing the sedentary percentage for that participant, it's not going to use that in the total correlation that's run. And so that's actually the parameters that we need to use. So here's the correlation. And again, if I were just to run this correlation, giving me a correlation coefficient for my sedentary percentage and age and our p-value for that correlation for sedentary percentage and age, and I try to run this without the additional parameters, it's going to give me an NaN. Okay, because we have not a number incorporated, we need to add an additional parameter here that's saying that I want to just only take the complete rows. So I'm going to rerun this, and I can see that a correlation coefficient is 0.1550, and the p-value associated with that correlation coefficient is 0.28. And so this is not less than p is equal to 0.05, so there should be no significant correlation between age and sedentary percentage. And just to make sure that that's the case, and just to visualize that, I'm going to go ahead and plot those data. Here I'm just plotting on the x-axis age, and on the y-axis sedentary percentage, and all of these types of code should be familiar to you. Great. So now I have my age and 3, 4, and 5-year-olds, and the sedentary percentage along the y-axis. I want to show you something additional that we can do, which is fitting a regression line to these data, just to get an idea of what the relationship is between these two variables. So here I'm going to go to Tools, and I'm going to go to Basic Fitting, and it's going to create a little pop-up window, and it's going to select data 1, which is all of our data that we have, and we can select a linear analysis, and it's saying that all the data points with NaN will be ignored, which is what we did before. So we have our regression equation, which is just a linear regression equation, and you can actually create this regression using just a fit linear regression in the next section. And so it created our line, and it created our regression, and all of that looks good. And I'm just going to change that line width to 2, and I'm going to change the color of that to black. Okay, so I just showed you how to fit a linear model manually. So now I'm going to show you how to actually do that using the fitlm function. So here, let's look at the fitlm function. Okay, so the fitlm function takes input that could be a table or an X value that specifies a linear regression model. This can seem a little bit more complicated to look at because the output is a variable that's a structure called MDL. And again, you can name that whatever you want, but that structure has a certain parameters or characteristics that sometimes can be hard to follow. So we're gonna go straight to the examples just so you can see how this is done. So I want you to go through and just get an idea of what the fitlm function does. Here, there are 3 parameters in the workspace. X is weight, horsepower, and acceleration. And then in the workspace, there's also an MPG, or miles per gallon. As is, what this does is it fits these 3 predictors to estimate miles per gallon. And so you can see that. You can also get an idea of the coefficients of the different components of that model. Okay. So there are a lot of different parameters in here for the normal stepwise linear regression. The one that I think is the most helpful for us is actually this format. So we insert a table and we actually designate what we want the model to look like. So in this case, it was just we're predicting miles per gallon based on two variables or two factors, weight and acceleration. So that's pretty close to what we actually want to accomplish in our codes. So let's take a look at our codes here. So here we're going to have our table, which is our PA data for week 1 for Tuesday, Thursday. And the variable of interest that we're using as our Y variable is our SED percentage. And we're predicting that based on age. Now, again, based on the correlation coefficients that we saw using the core function, this is not a statistically significant relationship. So I'm going to go ahead and run that here. And here's our output. So we can see that there is an intercept value and there's also this age value. And we can see that that p-value for the age estimate is not significant. But one thing that's worthwhile to pay attention to is that the intercept and the slope variables here are what are actually used to create the statistical model or the regression. So here are the intercept and slope terms, and you can see that the intercept and slope terms are exactly the same as when we fit the linear regression just using the tool's basic fitting. So this is nice because that also helps to confirm that we do indeed have a non-significant, slightly negative slope. You can see that this is a negative 0.041 and a intercept at around 0.7. The other information that's useful here is that we also see our R-squared value. Our R-squared value should be our correlation coefficient squared. So let's go ahead and just do that real quick. So core SED age and this is squared, is equal to 0.024. So that all checks out, and we see that our p-value should be the same as the p-value here. So we see that's all correct. I just copied all the information for the output for the regression model, and I commented that out just so I have it when I rerun my codes, I can see exactly what was done. So the next thing I want to do is I want to run a t-test to see if there are any differences in sedentary percentages between the intervention and non-interventions, regardless of the classroom and regardless of week. So let's look real quick at the t-test function. So the regular t-test, just like this, does a one sampled or paired t-test. So there's only one sample, but there might be multiple values, which is exactly what we're interested in doing here. The basic t-test has 1 to 2 inputs, as well as some additional parameters, and up to 4 outputs. Let's look at this one, for example. So here we have our X and Y pair, and it outputs H, which is the hypothesis test of whether or not we should reject the null hypothesis. P is the p-value for that t-test. CI is a confidence interval, and stats returns a data structure that includes the t-statistic, the degrees of freedom, and the estimated standard deviation for the population. So we're going to go ahead and use this example, and you can go to the documentation and actually see exactly the examples that they show for more information. So the first thing I'm going to do here is I'm going to compare our sedentary percentages for our Tuesday, Thursday data for PA data. So that has exactly half of our data. And in that data set, we have all weeks of our intervention and all classrooms. So we're just going to compute a t-test just to see if this is different. I have renamed the different parameters. This is the null hypothesis for Tuesday, Thursday versus Wednesday for sedentary percentage, the p-value, the confidence interval, and that statistical structure. So here's our output. First, we see that we reject the null hypothesis, and we can see why that's the case because p is less than 0.05. And another way of testing that is that the confidence interval does not include 0. So it goes from negative 0.13 to negative 0.047. And then the t-statistic that's associated with that test is negative 4.17, which is pretty large. And our degrees of freedom is 133. That's a pretty nice difference between those two. It's also nice to go ahead and plot that. So that's what I'm going to do here. Before I plot that, the other thing that's important is that when we're computing statistics, we're taking the difference between those two means, and we're also considering the variance. And a measure of variance can be standard deviation, but oftentimes we're going to use standard error. So one thing that we need to do is we need to compute the standard error of the mean, which is going to be our standard deviation of the value for Tuesday, Thursdays, and it's going to be divided by the square root of n. So in order for us to figure out what the total number of data points that are actually going into that calculation, we have to figure out how many are going to be NaNs. So in order to do that, we are going to use the command isNan. And what that's going to do is it's going to give us a set of zeros and ones that correspond to whether or not the data in a particular row is or is not an NaN. So if it gives us a 1, that means it's an NaN. So what I can do is I can add up all the ones, or add up everything in that column of data, and that should give us the number of NaNs that exist in our file. So if I were to look at the size of data set 1, this should be 260. So size of PA data, Tuesday, Thursday, for the number of rows should be 260. And then the sum of the NaNs is 96. So if I take the difference between that and take the square root of that, then that will give me my denominator for my standard error. So if this doesn't make sense, we can go through this in class. But I'm going to calculate my standard error. And I can see that they're both quite small for both Tuesday and Wednesday. And now I'm going to use a bar plotting command to be able to create a bar graph where it's going to plot the data from sedentary percentage for Tuesday, Thursday on point 1, and data for the sedentary percentage for Wednesday as point 2. And it's going to have the face color of the bar as white, but with black lines, and it's going to be pretty thick. And then overlaid on top of that, I'm going to use the error bar command, and my X positions are going to be the exact same thing as my bar. My Y positions are going to be the exact same thing as my bar. And I just have one more parameter in here, which is the size of the error bars, which I'm going to set as my standard error of the mean. And so I'm going to change my X ticks in this last line of code for that 1 and 2 to correspond with the intervention and non-intervention days, because I'm plotting the Tuesday, Thursday data on 1, which is the intervention day, and the Wednesday data, which is the non-intervention day, on 2. So here's what that looks like. Perfect. And the last thing that I want to do to make this a little bit more manuscript ready is I want to create a line at the top of this bar graph that indicates the degree of statistical significance. So I'm going to go back and take a look at what that level of significance was. So that was P is less than 0.00005. I'm going to use 3 asterisks, and if I look at that figure again, I'm going to create a line that goes from 1, which is right here, over to 2, and at a height of about 0.55, okay, so it's going to create one line there. And then right above that, just right off center, I'm going to create 3 asterisks. And there's a little bit of playing around in terms of the location of that line and the asterisks. And so here's what that looks like. Just like that. And let's say I want to give us a little bit more space between that bar and where that line is. I'm just going to replot that, but I'm going to put my line just a little bit higher. So I'm going to put it at 0.56, and I'm going to replot that. Cool. So now I have a figure that captures everything that I want. I might actually want to give a little bit more space, and I might want to cut off the axes just a little bit. So I have a slightly tighter figure. So I'll just go ahead and do that as one last step. So my x-axis, we're going to go to 0.25, and we're going to go all the way over to 2.75. That should capture the full range without going too far. And I'm going to go from 0 to 0. Let's say 65. Perfect. So that's what our figure looks like, and I think that looks pretty good. Okay, you can export that figure as whatever kind of data type you want. So you can go to Export Setup, and you can change your rendering. A lot of the times they're going to want it to be at least 600 dpi. So you're going to apply that to your figure, and you're going to export that as whatever type of data file the journal wants. So sometimes they want EPS files, so we're going to save that as EPS. I'm going to call this figure 1, and this is going to be our said by age. Okie doke. So the next thing I want to do is I actually want to run a repeated measures ANOVA to see if there's a difference between our intervention as a function of time. So does the sedentary percentage decrease across the different weeks of our intervention? And right now, what we're going to do is we're going to separate out the sedentary percentage for each of the different weeks, but in order to run the repeated measures ANOVA code, we actually have to stack it in individual columns. And so the way it's done right now is that each week of data is just added to the different rows. And so I'll rearrange these data a little bit so that it's in the format of interest. So I'm creating a new variable called said% by week. We're going to pull the data from PA data, where our week of the intervention is the first week, and I want to pull all of these columns because that's helping me to identify some different demographic data that is going to be useful. And column 13 in our PA data set is our sedentary percentage. So it's taking all this information here, columns 1 through 6, and then it's also taking weight, age, and gender, as well as a sedentary percentage. And you can see that here. So I'll open this up. Perfect. So said% by week now has 10 columns of data, and you can see sedentary percentage is just for the week, for week 1. We are missing a little bit of data. And now I'm going to add columns to columns 11, 12, and 13, and 14 that represent week 2, 3, 4, and 5. And so in order to do that, I'm going to create a new variable, so sedentary percentage, or said%2, and that's going to be equal to our PA data with our week of the intervention equal to 2, and again for column 13. And the reason why we're using these curly brackets is that I'm creating a new variable that's just numbers, and so again, we want to extract just the numbers. If I have just the regular parentheses around PA data, it would actually create a new variable that's a one-by-one table, and that's really not what we want. So I'm going to update this code to then add sedentary percentage for week 2, 3, 4, and 5. Perfect. And when I look at that data set again, I notice that for sure week 3 is missing a boatload of data. And so what I'm going to go ahead and do is I'm just going to delete said%3. And the last thing I'm going to do before I run the repeated measures ANOVA is I'm going to set the day of the week variable, which says whether or not we're in an intervention day or a regular Wednesday, to a categorical, because if it's just a numeric as it's written right now, it'll model the day of the week a little bit differently than what we want it, and we want it to be modeled as a categorical. Okay, so now we're actually able to run our repeated measures ANOVA. One of the things that we need to add is a variable that defines the number of repeated data points. Now, if you actually go to the fit RM codes, the best thing to do is to actually look at the example. You can basically copy exactly what it's doing here in order for you to see the repeated measures model run. The first thing I've done is I've, again, defined what our repeated measures are. We have 4 weeks of data. Remember, we got rid of week 3, and we're calling our variable name week. And the first parameter is going to be the table that we're working with, which is our said% by week. And then we create our model in which our first sedentary percentage for week 1 is subtracted from the sedentary percentage from week 5 and every value in between that. And then it says that it's going to try to predict whether or not those things are different based on the day of the week. And our within measures design, which is basically our repeated measures, is defined by this variable mesh, which we just made. So I'm going to go ahead and run this. If it runs, you should be able to see the coefficients relating to the equation that defines the repeated measures model. So we have an intercept term, and then we have an adjustment that's based on the day of the week equal to 1, which is Tuesday, Thursdays. So we can see that here. And I just copied it and commented it out just so I have it. And then I'm going to create an ANOVA table, which is going to give us the information about the main effect of week, as well as our intercept, which is constant. So we can see here that the day of the week, either the intervention day, Tuesday, Thursdays, or the non-intervention days, Wednesdays, are in fact different and statistically significant. And I'm just going to copy and paste that into the codes. And then I'm going to look at the repeated measures. So here, this shows me whether or not there's a main effect of week, which there is, and there's an interaction between day of the week, and there is. So again, you would copy the codes there. And you have to also, of course, test for your assumptions. One of the assumptions for repeated measures models is sphericity. So you're going to run the Module6 test. And again, in the example provided in the FIT-RM and also under the repeated measures model in the statistical toolbox, you'll see that this is one of the next things that it asks you to do or suggests that you do. And so because this value is greater than 0.05, we have not violated the assumption of sphericity. So we are good to go. We do not need to use the Greenhouse-Geyser corrected p-values or the Heuenfeld corrected p-values. We can just use the regular p-values that are here. Awesome. We can use, once we've run our repeated measures model, we can actually create our means and standard errors, the means, using this group stats function. So again, you would go up to group stats, and this is again within the statistics and machine learning toolbox. And there's a bunch of different inputs and outputs that can be used. Go ahead and work your way through to see the examples here. But what I'm basically going to be doing is I'm going to put as my input the repeated measures model that we've been working with. The two variables that it's going to compute means and standard errors for are going to incorporate week and day of the week. So week 1, 2, 4, and 5, and either Tuesday, Thursdays, and Wednesdays. And it's going to output the mean and SEM for each of those combinations. So let's take a look at what that means. So here's what that looks like. So week 1, day of the week 1 is Tuesday, Thursdays for week 1. And week 1 for day of the week equal 2 is Wednesdays for week 1. So now I can take this table and I can create my bar graph and my error bars so that I can represent the days of the intervention by week. And this is going to be a little bit fast, so we'll go through this a little bit more slowly when we have our lab section. But that's the basic plot that's created. The white bars are going to be our Tuesday, Thursday data, and our red bars are going to be our Wednesday data. And I know that because I've marched through this day by week means an SEM variable I created, and I saw that all of the odd numbers are going to be the intervention days, and all the even numbers are going to be our non-intervention days. And again, this is just an elaboration of the bar and error bar codes that we ran above. And then I'm going to add my X and Y axes to this. Perfect. And I can see that now I have a pretty nice figure that shows the days of the week. The only thing that I am missing here are, of course, my lines and asterisks that are indicating what's actually statistically different. And so when I'm looking at this analysis, what I see is that for the intervention days, we see that sedentary percentage seems to decrease as a function of week. And we slightly see a similar kind of decrease for the non-intervention days, but this increase up here suggests that we don't have a clean linear decrease across time. So we can use the mult compare function to compute all of the differences for each week by the Tuesdays or Thursdays. So what it's going to do is for Tuesdays and Thursdays first, it's going to compare each combination of weeks. So week 1, week 2 for Tuesday, Thursdays, week 1, week 3 for Tuesday, Thursdays, and then it's going to do the same thing for the Wednesday data. So week 1, week 2 for Wednesday, week 1, week 3 for Wednesday. It's going to compute those differences and the standard error for those differences, as well as the p-value and the confidence interval. What I can see already is that I have one combination here, which is Tuesday, Thursdays comparing the second week and the fourth week. So Tuesday, Thursdays, second week versus the fourth week. So those two are different, which is nice because we would expect that there would be a decrease across time. And then the next significant value is going to be week 1 and week 2 for our Wednesday data. So those two are statistically significantly different. And then the next one that we see, that's it. Those are the only two. Those values aren't necessarily as meaningful as if we reran that mult compare, but instead of comparing within each intervention day, if we actually compared the two interventions by week. And so that's what I'm doing here. So I'm going to compare the weeks by each day. Okay, so here what we see is that week 1 is different between the two groups, and week 4 is very different between those two groups. And week 3 kind of approaches statistical significance. And the degree of significance for the first one is probably, it's not less than 0.001, but it is less than 0.01. So I'll give that 2 asterisks, and then this one is 3 asterisks. And again, we're going over and on top of week 1 and week 2 is different for those two, and week 5 is different for those two. And so we're going to go ahead and plot that on top. And that's what this looks like. I'm going to make this a little bit bigger. And if we wanted to, we could increase our axes on the top just a little bit and add a legend. And so now this is what figure 3 looks like. I'm going to pop the legend at the very top. And that's our figure. So this could be, a publishable figure as is. You can tweak exactly where the location of the lines are and the asterisks. You can change the location or the orientation of the legend. So let's say we wanted to take that and move that over here, or personally, I think it's probably better horizontal in the middle. But this is basically a publishable figure. So again, you could go to File and Export Setup. I can set it so that my rendering has 600 dpi. I apply that to my figure, and I can export this as figure 2. And this is going to be RM ANOVA. And this is said by week, by day. Okay, cool. So that's that figure. So I have run a full analysis examining correlations, regressions, repeated measures ANOVA, and t-tests. And so the last thing I want to do is I just want to save my data variables in my workspace as PA data stats. And I'm going to save my codes just to make sure I know that I have everything run. And what I'd like you to do is go very carefully through each line of these codes and make sure that you know exactly what these codes are doing and feel comfortable with each of these different functions. Again, we could have run just a regular ANOVA on some aspect of these data that we thought might be interesting, For the sake of time here, we're just going to focus on the kind of more complicated statistics that are very common that you guys will run. Okay, so just to recap, what we did today was we looked at our PA data and we ran correlations, linear regressions, t-tests, and repeated measures ANOVAs, and examined different aspects of those data and plotted those data. So we created summary statistics and figures that reflect significant differences that can be used for manuscripts. And in order to run all of these different functions, we had to sort our data, select our data, create new variables, and so forth. For the practice problems for Module 6, you are going to just build upon your understanding of these specific codes and run different aspects of these codes to examine differences between different weeks or differences by age or other variables that might be relevant to analyzing these data.